Hi everyone, in this section we're going to talk about oblique triangles and the law of sines. We first have to talk about congruence axioms when we're talking about these triangles. We're going to be solving triangles, which means we have to find all three side lengths, like how long each side of the triangle is, and then all three angle measures. But in order to find all six of those things, three angles and three sides, we have to know some of them to start with. And so given a few pieces of the triangle, like for example, two sides and an angle in between, we can find the remaining pieces of the triangle. And we can find what's called a congruent triangle, which means it has the same side lengths and same angle measures. So first, side angle side is if we know two sides and the included angle. So notice in this picture, we have a side B and a side C, and then the angle A is what's connecting them. So that's why it's called the included angle. So if we know this side length of the triangle, this side length, and then this angle in between, we can actually find the missing three pieces of the triangle just based on that given information. Similarly, there's angle side angle as a congruence axiom. So if we know two angles and the included side, we can find the other three pieces. So here's angle A as an example, side C, which is connected with angle A, it's touching it if you want to think of it like that, and also with angle B. So two angles and then the side connecting them. If we know that information, we can find the missing pieces. And then the other one is side, side, side. If we know all three sides of the triangle, we can find all three angles as well. So an oblique triangle is just a triangle that's not a right triangle. So basically up until this point in trig, you've only dealt with right triangles. And so now we're officially learning about, well, there's other types of triangles out there, they're called oblique. And so we're going to find out information about these triangles now. Now, in order to solve an oblique triangle, we break it into four different possibilities. We call them cases. So case one side and two angles are known. So this will be given to you. You're going to be told what one of the side lengths are and then two of the angles. And so there's two breakdowns of this. It could be side angle angle, so a side, an angle touching that side, and then the next angle, like if you're thinking about like traveling around the triangle, or an angle, the side touching it, and then the very next angle. Case two is if you know two sides and one angle. So your SSA, so you're given a side, another side length, and then another angle. But notice it's not the included angle. So this case two is the angle not between the two sides. And then this case is actually pretty special. There's a whole section that we're going to go through dedicated to case two. Case three is if you know two sides and the included angle, so side angle side. So notice cases 2 and 3, you're given the same information, two sides and one angle, but it just depends on where the angle's at. In case 3, it's the included angle, and then in case 2, it's the not included angle. And then case 4 is side, side, side. You know all three side lengths. So we're going to learn in this section, in the next section, 7.1 and 7.2, the law of sines. And those can be used to solve cases 1 and 2. So if you're given this type of information about your triangle, you're going to use the law of sines. We're specifically going to focus on case 1 for this section, and then in the same video a little bit later we're going to focus on case 2, which is technically the next section. Then the law of cosines, which we'll learn in another video, is how you solve cases 3 and 4. Note that if there are three angles of the triangle, we can't find a unique triangle. And if you think about it, if you know all three angle measures, you can have any size triangle with those angle measures. So you can have like a really tiny triangle, like let's say all the angles are 60 degrees, so it's equilateral, it's like a very evenly looking triangle, and it's tiny. But you can also have a huge triangle with all angles 60 degrees. So AAA is not a congruence axiom. Here's information about how the law of sines is derived. I'm not overly concerned that you know how to derive the law of sines, but I did want to show this to you. So feel free to pause this and take a look at it if you're interested in how the law of sines was developed. So here is the law of sines, and this is it right here, this equation. In any triangle, ABC, so the triangle is named based on the angle measures, capital A, capital B, capital C, with sides little a, little b, and little c. This is true. So just to make it very clear before we start getting into the problems, capital letters are going to be reserved for angle measures, and lowercase letters are going to be reserved for side lengths. So if you see a lowercase b, it means it's a side length. Capital B means it's an angle measure. So this ratio, side length A divided by sine of A, is the same ratio as side length B divided by sine of B, and the same thing for side length C divided by sine of C. There is an alternate form of this if you just flip over the ratios. So sine A divided by side length A, and so on. And it honestly just depends on what you're given in your problem, which version you're going to use. Okay, so let's take a look at our first example here. Solve triangle ABC if angle A is 32 degrees, angle B is 81.8 degrees, and side length A is 42.9 centimeters. So just a real quick note, even if the degree symbol, like let's say we didn't see it, we would still know these were angles because they're capital letters, capital A, capital B. And even if the centimeters was left off, we would know 42.9 is a side length because this is a lowercase a. So here's a drawing, a potential drawing. You know, it might not be to scale exactly, but you could draw a rough sketch for yourself whenever you're given the information for solving the triangle. It might help you solve the rest or see what you're looking for. So in any triangle, whenever you're told to solve a triangle, it means find all 6 pieces. So notice we have one angle here, A, and we have another angle here, B. We are missing angle C. So that's one of the things we're missing. We know one side length A, but we're missing side length B and side length C. So we're missing 2 side lengths. So we know 3 out of the 6 pieces of information to consider this triangle solved. So we're going to take a look at our law of sines, and you have to pick out the ratios here that are going to help you based on the information you have. So notice what we're given. We're given information about angle A and angle B. We don't know anything about angle C just yet. We also know something about side length A. So we definitely have to use this first ratio, A over sine A. Now because we know angle B, we have to pick this ratio as well, little b over sine B. We don't know anything about C, so we're going to leave this one off for now. We'll figure out C later. So we'll start with what we have given, like the given information. So we're starting with this ratio, this proportion now. Okay, so you fill in what you know based on what was given. We knew what little a was, 42.9. We knew what capital A was, 32. We also knew what capital B was. And now this is just a proportion, or this equation, and you solve for what you're looking for, in this case B. So if you want, you can try to pause it and solve for B. Basically, you're isolating B, so times everything by sine 81.8. Okay, so little b is alone. You solve for it once you times by this denominator. And then using your calculator in degree mode, you'll get that this is about 80.1 centimeters. So now we found one of the missing pieces. We now know side length B is 80.1. So now we need to find the other 2 missing pieces, which was little c, side C, and then angle C. Okay. Now the third angle is easy to figure out just because of the fact that when you have a triangle, all 3 angles in a triangle add up to 180 every single time. So if you know 2 of the angles, which we did know, we can find the third one very quickly. We solve this equation here. If you want, you can break it down ahead of time. Isolate C by subtracting A and B, and then fill in what you know A and B equal. So C is 62.6 degrees. And so now we have the next missing piece, and the last thing we were missing is side length C. Okay, so we're going to go back to our law of sines to find the side length C. So we're now going to use this ratio, little c over sine capital C. And now, based on what we were given, we technically have 2 choices here. We can use sine A, little a over sine A, little b over sine B. but you always want to go back to the given information as much as you can. So since we had to calculate little b, let's not use that. Let's use the given information. We were given everything about a, so we're going to use little a over sine a equal to little c over sine c. So we fill in what we know. We were given information about little a and capital A, and we just figured out what angle C or capital C is, and then you solve this equation for C. So just like we did for B, times everything by the denominator, and then in your calculator, you're going to get that C is about 71.4 centimeters. Sorry, 74.1 centimeters. This triangle is now considered solved. So the triangle is solved when you've found all three angle measures and all three side lengths. Once you have all 6 of those pieces, you're done. It's considered a solved triangle. Now, this is going to come up a little bit later, but things should line up, and what I mean by that is, so your smallest angle here is 32 degrees. That should be across from your smallest side, which was 42.9, which, yes, that was the smallest side. Your biggest angle, in this case it was 81.8, should be across from the biggest side, which it is, 80.1. And so that's a good way to check. Just make sure everything is lined up. Smallest angle is across from the smallest side, biggest angle is across from the biggest side, and then by default, the medium angle is across from the medium side. Now I mentioned this when we were solving, but I just want to make it very clear. Whenever possible, use given values in solving triangles rather than values that you come up with. Okay, so anything that was given to you, you want to use it as much as you can rather than things that you found, rather than things that you calculated. Because unless you type in the entire expression over and over again or keep it saved like in your calculator screen, there's going to be some rounding errors if you use your solved for values too much. So whenever you can, go back to what was given and use that over and over. All right, let's try this next example. John wishes to measure the distance across a river. He determines that angle C is 112.90 degrees, angle A is 31.10 degrees, and side length B is 347.6 feet. Find the distance we're calling A across the river. Okay, so we know this angle measure was C. We know this angle measure is A, and we know that if you know angle B is over here, this side length, this is little b. And the question is, across the river, how far is that? And that's what we're calling A. Little a is across from angle A. Okay, and so we have 3 pieces of information, and notice what we have. We have angle, side, angle. So we have ASA. Okay. All right, so we're going to find the measure of angle B, and then that's going to help us find our missing piece A. Okay, so we do know 2 of our angles, so finding the third angle is easy, knowing that they all add up to 180. So we just subtract our given values for angles from 180, and we know B is 36 degrees. Now we're going to go to our law of sines to find our missing side A. Okay, so remember we just mentioned it. You want to use your given information as much as possible. And so we only actually know one side length, so we have to use this. So we have to use little b. So we're going to use capital B, our angle B, and then little b. And this is going to be to find side A. We didn't know anything about side C yet. We only knew angle C, so we couldn't use that ratio for our equation. Now we fill in our given values and then our found value of 36 degrees, but this was exact because we had exact values given for our angles, and then we solve for a little a. So times both sides of this equation by the denominator, sine 31.10. And so here's what a is exactly, and then in your calculator in degree mode, it's approximately 305.5 feet, and so that represented the distance across the river, 305 feet across. Our next example, 2 ranger stations are on an east-west line, 110 miles apart. A forest fire is located at a bearing of north 42 degrees east from the western station at we're calling A, and then a bearing of north 15 degrees east from the eastern station at what we're calling point B. To the nearest 10 miles, how far is the fire from the western station? Okay, so I would encourage you to pause and try to draw this setup based on this information. I'll show you in just a second, but feel free to pause this and try to draw it before I show you. Okay, so here's our drawing. Of course, your student have to have all these animated parts, but for our bearing for station A, we had north and then 42 degrees to the east, and that's going to be for angle A. Okay, now angle A is not 42 degrees. Angle A is inside the triangle. The 42 degrees is actually outside. Okay, for the next station B, from north, we went 15 degrees east, so that's right in here. And so angle B is also inside the triangle, which we don't have that just yet. And then we do know that they're 110 miles apart, so we know this length here is 110. So we actually don't have angles A and B, even though we might have thought, oh, maybe we have them from this bearing information. We still have to do a little work to find them. Okay, so first find the measures of the angles in the triangle. So inside the triangle is angle A, and inside the triangle is angle B. Now angle BAC, meaning that's angle A technically, the measure of angle BAC. So BAC just represents angle A, is this 90 degrees. So notice you have it form a 90-degree angle with north and east, and then you take away the 42 because angle A is what's left over in between. So that's this setup here. So we know angle A is 48 degrees. So in here, this leftover between 42 and getting all the way down to 90 is 48 degrees. The measure of angle B, so ABC, ABC is just angle B. It is a 90-degree angle from this line to north, and then plus 15 more because this leg of this triangle is 15 degrees east from there. So it's 90 plus 15, so angle B is 105 degrees. Okay, so we found our angles, and then we can use those two to find the last one. Angle C is just 180 minus the 2 we know, so angle C is 27 degrees. So we now know all three angles of this triangle. Now what we're looking for is side length little b, and that's because the question says how far is the fire from the western station, so the station further west, which is station A. So we're going to use our law of sines for this, and we know angle B, we know angle C, and we know little c. Little c is this length 110, which is across from angle C. Okay, and so we're going to use the plug in our given values and solve for what we want. We figured out that angle B was 105, we figured out angle C was 27, and then we knew length C was 110. So times both sides by the denominator, sine 105. And so that's what B is exactly, and then rounded is 230 miles because we were told to round to the tens place. Okay, so it's approximately, the fire is 230 miles from this western station. We're going to talk about area of a triangle just for a minute now. Since we're talking about oblique triangles, our area of a triangle formula has to get a little bit modified from what we're probably used to. We're used to the formula for right triangles, which I'll remind you about it in just a moment. So our area formula, we have three different versions depending on what we know, but it's all very much the same. It's 1/2 times the product of two sides times sine of the angle between those sides. So if you draw this triangle, side A and side B, the angle between them is angle C. Same thing here, side B and C, the angle between those is angle A. And same thing for AC and then capital B. So these are different versions of your area of a triangle formula, and you pick which one you're going to use depending on what's given to you, which given information you know. Now this is what I was mentioning. The most familiar version is for right triangles. So if the measure of the angle is 90 as the included angle, so let's say C is 90 degrees, or A is 90 degrees, or B is 90 degrees, then it's really a right triangle. And then sine is 1, and it just becomes 1/2 base times height, where height would be the other side length. Like in this case, it would be C, or in this one, it would be little b. We'll try an example using our new area formulas. So find the area of this triangle. Basically what you have to do here is just identify what you know. So this is angle A in this corner. So that means this side length, 34 feet, is little a. Okay? So it's always across from the angle. That's how the naming is done. So this is little a, is 34 feet. Here's angle C up top. So that means this is side length C. So 42 feet is little c. And then this is labeled as B, so this is definitely angle B. So we're going to use this version of our area formula because we know side lengths A and C, and we also know angle B. And so we just fill in all three of our values into our formula. Okay? And then at this point you can use your calculator. If your calculator doesn't do degrees and minutes, you can just take the 10 minutes and divide it by 60. And so you could say 55 plus 10 over 60 degrees, and that would give you the same value. And it's about 586, and then it's area, so it's square feet, because technically this is 34 feet times 42 feet, so it is square feet. Now we're going to continue, but technically this is the next section. This is 7.2. It is still the law of sines, but it's going to be about what's called the ambiguous case. So this is case 2 out of our 4 cases. So we just did some examples in 7.1 dealing with case 1, given one side and then 2 angles. And now we're going to focus only on case 2, which is called the ambiguous case because of the possible answers, possible outcomes. And we'll get through that. We'll talk about what that means. But in this case, we know 2 sides and then another angle, but it's not the included angle. Now the ambiguous case, or case 2, since we're given the lengths of 2 sides, but then an angle that's not included is considered the opposite angle of one of the sides, we don't know very much about the triangles. We know enough to solve, but it leads to different possibilities. You can have 0, 1, or 2 triangles that actually satisfy the given information. And so, for example, in this picture, let's say we know side length B, and then we would know maybe side length C down here. But the angle opposite means it's not angle A, it's not the included one. So it's either we know C, capital C up here, or capital B somewhere down here. Now, depending on the size of the missing side, we have a lot of possibilities, and we'll go through that in the next slide. So we're going to start with if A is acute. There's actually 4 possible outcomes. Now, the number of triangles here on the left is what I was just mentioning on the previous slide. Based on case 2 information, you might have no triangle. So what's given to you when you try to solve, there's actually no triangle that has those like measures, those side lengths, that angle measure. Or there's exactly 1 triangle that has that information. And then the other possibility is, well, there's actually 2 triangles that, based on what was given to you, the given information, 2 sides and an angle, there's 2 different triangles that might work with that information. So if A is acute, so less than 90, and sine of B, you figure out that sine of B is greater than 1. Well, remember this, the range for sine is from -1 to 1, so this is not possible. Sine of an angle is not going to be more than 1. So that's why this doesn't work. There's no triangles. If you figure out in your calculation sine of B is greater than 1, then no triangle. And just a quick note, I'm just sticking with B here for this example to break it down, but depending on what is given to you, this letter might change. So you just have to adjust accordingly. Maybe it's sine A or sine C, depending on what's given to you initially. Now, when there's 1 triangle, either sine of B is exactly 1, which just makes a nice right triangle, Or sine of b is less than 1, so between 0 and 1, but then we know that side A, we figure out that side A is longer than side B. The two triangles comes up also when sine of b is less than 1, between 0 and 1, but side A is actually smaller than side B. And we'll go through the process of how you figure this out. So you don't have to memorize this chart. I'm just sort of showing you ahead of time the possibilities and how you start to figure out how many triangles you have, 0, 1, or 2. Now I just want to clarify this drawing down here. The reason why you have two triangles, if side A is smaller than side B, well, this leg of side A, it can kind of like, think of it like swinging inward toward the triangle. You can have like this little wedge looking triangle if side length A is shorter than B. But then also if side length A is longer, think of this leg as swinging out, like swinging to the right. And so it forms this bigger triangle, like it looks bigger. But in both drawings, because there's technically two triangles in this drawing, A is the same length in both of them, but it just, the triangle shape is different. So this one kind of looks like a little wedge, and then the whole thing looks more like this drawing up here. Okay. Now also, if A is obtuse, there's two possible outcomes. So 0 or 1 triangles. Again, if sine of B is 1 or more, and you know angle A is obtuse, meaning greater than 90, then this is not going to exist. There's no triangle. Sine of B equal to 1 would mean that A is exactly 90, but because we know it's obtuse, then this can't exist because we already know A is bigger than 90. There's 1 triangle. Again, if you know that A is obtuse, this angle is big here, bigger than 90, and then your sine value makes sense. You have a sine between 0 and 1, and then you know side length A is longer than B. So remember we talked about this in a different example earlier. The biggest angle has to be across from the longest side. So this is possible. You do get a triangle if you know this angle is big, the biggest angle, and this is the longest side, then this is definitely a possible triangle. When applying the law of sine, you want to think about a couple of things. For any angle theta in the triangle, the sine value has to be between 0 and 1 for it to exist, for that angle to actually be part of a triangle. If sine of theta is exactly 1, then we know that the angle is 90 degrees and you have a right triangle. Sine, we also know another fact is that sine of theta is the same as sine of 180 minus theta. Supplementary angles have the same sine value. This is going back to your unit circle, so let's just review really fast. On your unit circle, let's focus on, like, let's say 45 degrees. The sine value of 45 degrees is square root 2 over 2. But across your unit circle into quadrant 2, sine of 135 degrees is also square root 2 over 2. This is true for 30 degrees as well. Sine is 1/2 across your unit circle. At 150 degrees, sine is also 1/2. So the thing is, what's going to happen in these triangles when you're trying to solve with this ambiguous case, you're going to have two possibilities that you have to look at. Well, maybe if my angle is 30 degrees, I know my sine value is 1/2, but maybe I have another triangle where the angle is 150 degrees, because that's going to give me the same sine value of 1/2. So that's going back to here, we have to consider this possibility that sine of theta is the same as sine of 180 degrees minus theta. And then third, the smallest angle is opposite the shortest side, the largest angle is opposite the longest side, and the middle valued angle is opposite the intermediate side. And this is something I've mentioned a couple of times. So this is kind of just a check step. Make sure that everything checks out here. Your biggest angle has the biggest side across from it, and so on. We're going to try this example. Solve triangle ABC if B is 55 degrees 40 minutes, little b is 8.94 meters, and little a is 25.1 meters. Okay. Now we're going to use the alternate form of the law of sines. The reason why we're flipping over our law of sines is just because what we know and what we want to know. And so let me clarify that. We know two side lengths and one angle. So we want to know another angle. And by flipping over our law of sines, we're putting the known stuff on bottom. So the two known side lengths go on bottom, and then what we don't know ends up being in the numerator. And that just makes it a little bit easier to solve. You don't have to flip this over, but it just makes your solving process just slightly faster. And so sine A is the thing that we're looking for. We know the other three values in this proportion. And so if we just isolate sine A by multiplying by 25.1, and then we plug that into our calculator, we get that sine A is about 2.3. Now, if you try to type in sine inverse now into your calculator, it's going to say error. And hopefully you can see why that's going to be an error. Sine of any angle is never going to be 2.3. Sine is between -1 and 1, and for our triangle values, it's between 0 and 1. And so this is not going to exist. So since sine A is more than 1, it's impossible. There's no triangle that's going to have that value. Let me just make a mention of this. I said it a couple slides back. In the chart, I use the letter B just to stay consistent with lettering, but just depending on what you're given and what you're looking for, you just use your letters accordingly. So in the chart, I had information about sine B was greater than 1, so it's impossible. So it's just sine A here because we're dealing with angle A. And now if you are wanting to see like why this doesn't work, if you try to draw this triangle, you won't be able to. You have angle B is about 55 degrees. And so if you think about drawing this, you kind of have to draw it accurately, somewhat accurately, to be able to figure out from the drawing if it's going to work. And by that I mean you have to kind of know that 55 degrees looks like this. We know that 90 degrees would be straight up from here. So 55 degrees is a little bit higher than halfway. And so this is a pretty good representation of what 55 degrees would look like. And so length 25.1, and this is all for your own scaling. If you're going to draw something that's supposed to be 25.1 meters, like let's say I draw it this length, then something that's 8.9 meters has to be way smaller. It has to be like a third of the length of 25. So when I try to draw side B, it's pretty small compared to side A. So there's no way I can make this connect to my other piece of my triangle. So there's no triangle that would work with these given values. Now let's try example 2. Solve this triangle knowing that angle A is 55.3 degrees. Little a is 22.8 feet and little b is 24.9 feet. Okay, so going right into our law of sines, we know two side lengths, so we're going to put those in the bottom of our fraction here. And we know angle A, so we're going to end up putting that in one of the numerators. And then we fill in our values and solve for the missing sine value. So I just kind of skipped a step from the last example. You fill in A and B in the denominator, capital A in the numerator, and then times by this denominator of 24.9. That's where this came from. Okay, so sine B is this quantity, and then in your calculator, that's about 0.897. So sine B is about 0.9 if you round this. And that's okay, that exists. Sine can be between 0 and 1 for our triangle angle values. Now there are two angles between 0 and 180 degrees that have this sine value. We talked about this with our unit circle. So because this sine value is less than 1, it does, or between 0 and 1, then we're good to move forward. The very last example we just finished, because the sine value was more than 1, we just stopped. We said, no, there's no triangle that will work here. So this one does exist, so we have to address the possibilities. So the first angle, when you find angle B here, you always just take the inverse. So sine of B is 0.897, so you can use sine inverse on your calculator, and you'll get that B is about 63.9. Your second angle, for the second possible triangle, you have to do the supplementary angle. So from our unit circle, if this angle is in quadrant 1, then we have to find the angle in quadrant 2 that has the same sine value, and you would do that by taking 180 minus the angle from quadrant 1. So your first angle, let me just say that one more time, you find that by just taking sine inverse of your value here. Your second angle, you have to find your first angle, okay, and then subtract it from 180. So 180 minus 63.9. So we have two possible angle B's. So I'm going to call them separately, B1 and B2. So because we have two different B values, 63.9 and 116.1, we have two possible triangles. And so we do actually have to work on both of these. Now, let's see what happens. A plus the second angle, B sub 2. We have 55.3 degrees, which was given for A, and what we found for B2, 116.1. Now, this is less than 180 when you add these, and so B2 does exist. Now, let me explain why this is even something we're considering. All three angles have to add up to 180. If you were to add up two of your angles and you got something more than 180, then that won't work. There's no way that there's room for a third angle. And so you just check. You say, okay, if I add up my given angle plus my found angle, can that even be possible? And because it's less than 180, there is room for there to be a third angle C. So we conclude, yes, B2 does exist. So we'll do another example so you can see this, that you have to check. Is this second B value, is this a possibility? Yes, it does exist because there's room between 171.4 and 180 for there to be a third angle, in this case angle C. So we have to actually solve for both triangles because there is in fact two triangles that fulfill the given information, and we solve for them separately. So we're going to start with what I call the one triangle. So the given A value, B sub 1, the first B angle, and then we're going to find the C angle corresponding to that B angle. All right, so we were given capital A, angle A. We were given little a and little b. B1 we found using sine inverse. So notice what's missing. We're missing our third angle, which we're going to call C1, and our third side, like little c1. Now we have two angles. The third one you just find from subtracting those two from 180. And so you take 180 minus 55.3 minus 63.9. And so our last angle is 60.8 degrees. So we have all three angles now. Capital C is 60.8 degrees. So then now we're missing side C. We're going to call it little c1. So then we use our law of sines. And notice what we're picking to compare it with. We're setting this equation equal to the value or ratio with a's in it. Because we talked about this at the beginning of the video, use the given information as much as possible. Even though we knew side length B and we found capital B, we're still going to stick with A because we were given capital A and little a. So we set up our ratio and our proportion here with our given information and our found information for angle C, and then solve for C1, little c1. So just times both sides of this equation by sine 60.8. All right, and then when you do that in your calculator, you'll get about 24.2 feet. So one out of the two triangles that fulfill the given information, we're done. We've solved it. We had these four values, sides A and B, angles A and B1. And then we found angle C1 and side C1. So triangle 1 is done. But we have to repeat this now for triangle 2. Now we solve our second triangle, A, B2, C2. So we're using our second B value, B2, but still the given three values, angle A, and little b. And then we have to find the missing values, which is capital C2 and little c2. So we're doing the same thing we basically just did, but with a different B value. So same process though. So we're going to find our angle C2 by subtracting our known angles from 180. And so we end up getting that angle C2 is 8.6. So C2 does exist because it is a positive angle value. And if you add these all up, if you want to just check, 8.6 plus 116.1 plus 55.3 do add up to 180. So C2, capital C2 we found, and now we just need to find little c2, side c2. Okay, so we go back to our law of sines. We're going to fill in what we know, and then solve for little c2. So we're going to times both sides of this proportion by sine 8.6. And then c2 is about 4.1 feet, 4.15. And so we've solved both triangles. So here's an image of our two triangles that we found. So let's just clarify why there was two, and hopefully it'll start to make some sense with this visual for you. We knew side B was 24.9, and we knew side A was 22.8. But based on how big angle C is, A could, you think of it as like sweeping outward, like toward the right here, or inward toward the left here. So when A was, angle C was bigger, called it C1, it was across from this bigger side C1, and side A kind of went outward toward the right. When C2 was little, it was across from this small side C2, and then side A kind of swung inward to the left. And so these two triangles, they have the same exact given information. Side B and side A, side B and side A, they're all the same lengths that we were told. Angle A is still 55.3 degrees in both of them. But then there's two possibilities for this last missing angle, either a small one or a large one, and then therefore two possibilities for this missing side length, a long side or a short side. So both of these triangles work and exist for the given information. So now that we've done some examples, let's just walk through the steps for how to solve case 2 triangles. The ambiguous case, knowing two sides, A and B in this case, and an angle opposite of one of those sides, so not the included angle. And so we can use law of sines to find the missing angle here. And so possibility 1, if applying the law of sines you get that sine B is greater than 1, well, we've talked about this, that doesn't exist, so no triangle will satisfy your given information, your given conditions. So once you find sine B, if it's more than 1, you just stop. You say there's no triangle that will work for the given values. Possibility 2, if sine B is exactly 1, then we actually have exactly one triangle, and we know sine of 90 degrees is 1, so B is 90 degrees, and it's actually a right triangle. Possibility 3, if sine of B is between 0 and 1, so this is the case, or the possibility that has a couple of outcomes, so you have to do a little bit of work here. You might have one or two triangles that satisfies the given conditions. So if your sine value of your angle, your missing angle B, is between 0 and 1, then you have to break this apart. So if sine B equals some value, so whatever this value you got that's between 0 and 1, we're calling it K. Then B1 is just sine inverse of K. Okay, so you just have, use your calculator and just say sine inverse of K is your first missing angle B1. Once you find the first one, then you find the second one by using the first B1 that you found, the first angle B. And you always just subtract that value, that angle, from 180. And that's how you find your second angle B. Now, when you find your second angle B, you find it by default. You find it by saying, okay, there might be two triangles, so let me just find my two angles for B. But you have to check, do you in fact really have a second triangle? And so you take your two angles, the one that you were told, in this case A, and then the one that you just found, your second angle B, and you have to check, is this really going to happen? If you add up your two angles, the given angle and the one that you just found, the second one, if it's less than 180, then yes, you do in fact have a second triangle. And that's because there's room for there to be a third angle here. A plus B2 plus C, you're missing C. If this is less than 180, then there's room for C to exist. If you add up your given angle A and your found angle B2, and it's more than 180, well, that's going to fail. There's no triangle where the angles add up to more than 180. So if you add up A and B2 and it's more than 180, then you don't actually have a second triangle. You could say no second triangle, I really only have one. So that's why it's one or two triangles in this case. So we'll try this out in an example. Solve this triangle given that A is 43.5 degrees, little a is 10.7 inches, and little c is 7.2 inches. Okay. So we're going to go to our law of sines, and we just pick the values or the setup based on what we are given. This time we're given little a and little c. The last couple of examples we were given little a and little b. And so we also know sine or the angle A, so that's good too. So we fill in what we know, and then we're going to find sine of C, sine of this unknown angle. So times both sides of this proportion by 7.2. And so sine of C, when you type this into your calculator, you get about 0.46. And so if this is more than 1, you can stop and say there's no triangle that would work. But this is between 0 and 1, so then we move forward. So sine of C is about 0.46. And so if you use sine inverse, so if you're just going right into your calculator and type sine inverse, you're going to get that C is about 27.6. But you have to be careful here. This is case 2, the ambiguous case, based on what's given. We were given two sides and a not included angle. So even though we just typed in sine inverse, so I've been labeling things as like C1, C2, things like that in other examples, but I'm specifically leaving it off here just to make sure you're aware. You have to be on the lookout for it. So I'm not done. I can't just say C is 27.6. There might be another C. So this other angle C is where we have the same sine value of 0.46. And we talked about how you get this one. You subtract 180 minus your previously found angle value. So 180 minus 27.6 would give us that our second C value, think of it as C2, is 152.4. So you want to always check, do I have two triangles? But then you have to do another check. So you want to start by assuming there's two triangles. When you find one, when you find your sine value, you take sine inverse. That's how we got the 27.6. But then you say 180 minus that angle to get your second angle value. So you assume that, and then you check, is this really going to happen? Am I really going to have two triangles? And so this one, we actually don't have two. We still only have one. And here's why. So side C is less than side A, okay, based on what we were given. That means that angle C has to be smaller than angle A. The sides have to match up with the angles. Remember I mentioned it, the smallest side is across from the smallest angle. And so for angle C to be so large, that means side C would have to be way bigger than A, have to be larger than A. And so it's not going to work just based on that fact alone. But you can also check by adding up the angles you do know. And so we knew that A was 43.5 degrees. If we add up this potential C2 value, it's too big. 195.9 degrees, that's not going to work for a triangle. The sum of the angles has to be 180, and so there's no way that this will cause us to have a second triangle. So that means we checked for a second angle for C. There's actually only one, so there's only one triangle here. So now that we did that check, we continue forward with just solving the one triangle. And so angle B was our last angle that was missing. So 180 minus what we found for C. Well, we were thinking as C1, but it's really the only C that actually exists, minus the given A angle. So B is 108.9, and then we find little b. So go back to your law of sines, and notice we flipped it back over to the original because we're looking for a side length. So we actually want what we're looking for back on the numerator. It's easier to work when we have it like this. So we fill in our given information, and then we're going to solve this proportion for little b. So just times both sides of this proportion by sine 108.9. And B is about 14.7 inches. And so you can double check now if you think about it with our picture and our information. Angle C, 27.6 degrees, is across from the smallest side. So the smallest angle, 27, is across from the smallest side, 7.2. Angle A is across, 43.5 is across from 10.7. Okay, that seems like it might be intermediate, but let's double check with B. So angle B was 108, and it was across from the longest side, 14.7. So yes, angle A and side A were the intermediate values, and then B, angle B, and side B were the largest values. So the largest side was across from the largest angle. Now our last example here is just to analyze without even actually doing any calculations. So without using our law of sines, just explain why angle A equal to 104 degrees, side A equal to 26.8 meters, and side B equal to 31.3 meters cannot be valid for a triangle ABC. So just prove, just by thinking about it, explaining why this triangle can't exist based on this given information. Okay, so look, we just sort of mentioned it a minute ago, but think about the sides across from the angles. So we know angle A is 104. It's pretty big, it's obtuse. And angle side A, if you notice, it's actually smaller than side B. So since angle A is obtuse, it has to be the largest angle of the triangle. You only ever have one obtuse angle in a triangle. You can't have two, because then they wouldn't add up to 180. It wouldn't form a triangle, the angle measures. So then A has to be the longest side. But right here we know it's shorter than B. So since we know that B was actually told to us that it's bigger than A, there's no way that this triangle exists.